Yeah, hey everyone, I'm Jack Gartside, and I'll just open this up by saying, please interrupt me at any point. Feel free to take photos, but I would appreciate if you didn't film the whole thing, and that's it. So, amazing. All right, so here we are. So, I'm going to talk to you today about making a physical Kolmogorov-Arnold network in some nonlinear SOI devices. So, quick hands up, has anyone heard of these KAN Kolmogorov-Arnold network things? Yeah, a bunch of you. Okay, cool. So I guess what I want to try to... So first of all, it's a really new thing. The project's been running for about 7 or 8 months in our lab. I'm really keen to get feedback, so any kind of comment, critique, anything, I'm kind of happy to have it. And I guess what I want to maybe propose to the community is that we have these really big sets of rich nonlinear dynamics in our systems, and they're often tunable. And I think a bunch of schemes have kind of played with that idea. But I guess what I want to show here is maybe we have something to gain as a community by directing learning maybe a little bit more explicitly onto kind of local per device or per node nonlinear reconfigurable functions. So cool. With that, let's get into it. So a little bit about my group. We're pretty new. We were set up around 9 months ago in Imperial College London. And we work across a bunch of systems. So here's the group. We had Toby give a talk on our nonlinear photonic work earlier in the week. And Max here has done a lot of the kind of underlying software and machine learning for this project. We're always looking for new PhD students, new postdocs, so please get in touch. And perhaps this is maybe the kind of 3 key strands of the physical systems that our group works in at the moment. So my background is a condensed matter physicist, really no learning to start with. We were interested in probably the closest thing to this so far is the previous talk, these kind of simple little elements of ferromagnet. But when you put a whole bunch of them together, we see some nice emergent properties, these different memory states, kind of various sort of emergent domain formation. And then we started to look at some computation in these, looking at the gigahertz resonances and how these change with the states. There's a bunch of papers on that. And then more recently, we've moved into nonlinear nanophotonic networks. And I guess the key thing here is that the materials that we tend to use are pretty simple, and most of the interesting stuff comes from how you pattern it up. And then this one is much newer, and this is what we're going to focus on today. So these are nonlinear silicon-on-insulator devices made by some collaborators in Italy, and we're going to see how we can use this big range of tunable nonlinear dynamics for some kind of computation. So here's a bunch of the papers. You can see we've been in magnetism for a bit longer, and this one's just gone up on Tuesday. There's a QR code there. The archive thing's processing, but it's on ResearchGate. And if anyone would like a preprint or a chat, we're really welcoming commentary on this one. So we're going to just have it as a preprint for a little bit longer before we submit to a journal. So happy to kind of hear anything from the community. All right. And for this project, so this is the team. We have myself and Max from my group, a bunch of collaborators from Italy. So Marco, who is in Milan, now in Turin, and Michele and Gabriele, who are in Agrate, the CNR lab that's attached to ST Microelectronics, and then Tom and Eleni from Sheffield, who did a lot of work on the machine learning framework. And then really big shout out to these two. So Fabiana Taglietti, who was Marco's students, now in ULIC, really worked on all of the initial IV characterization of these things that showed us they had these dynamics, and Andrea made the things. Cool. So that's everyone. Let's get into it. So what do we kind of typically learn in most modern neural networks? And I would say, please feel free to put your hands up if you don't think this is a fair comment, but generally we're learning big arrays of linear weights, and that's where most of the learning is taking place. The nonlinearities are often relatively simple, and they're fixed. And this actually underpins a huge amount of what we do. So I borrowed this from a talk from the original guy that came up with the CAN concept. But yeah, there's this little thing, right, of big matrices of linear weights that we multiply together. And if you look, so that little thing you might call a multi-layer perceptron. That's the kind of purest implementation, I guess, of that scheme. But actually, if we look at, more modern, more powerful, much bigger neural networks, under the hoods, kind of eventually, if you look close enough, that tends to be what's being learned and what's powering the system. So CNNs showed that you could take a perceptron and then bolt another slightly different set of linear weights on the front, and you could do much better with a kind of feature detection sort of processing. And kind of, I would say the same thing's happening in transformers too, these big attention heads, all that stuff. there's more modularity, more complexity, also much more of these linear weights, but it's really coming back to that. And, why has this emerged? So I want to point out three papers, think pieces, kind of commentary that I really like. So this one here is from some people in the audience, and if you haven't read these, I really recommend it. They're pretty short, they're really thoughtfully written, and they kind of spell out, coming from different angles, but I think overlapping quite a lot, why have we ended up with the sort of machine learning frameworks that we have today? So they argue, and I really agree, that basically what we might think of as these kind of like best, purest, most powerful algorithms may be that, but only, with the caveat that they're the best ones that make use of the most efficient or most scalable hardware we have today. And it turns out that GPUs and TPUs, even though they weren't really intended for this at all, are really good at linear matrix multiplication. And therefore, all of the things we want to do with learning tend to get kind of shaped into that shape. Also, because GPUs have been good for a while, there's been a tremendous amount of optimization from the machine learning theory and software community. So you have these kind of two-stranded things that have done amazing stuff, but have really kind of funneled us into this quite specific type of learning. And physical learning systems have often taken this approach too. So, there's a lot of fantastic work in the community from the group of Damian, amongst others, taking this idea of a big set of linear weights and putting them into resistive or memoristive crossbar arrays. We also see it in photonics. So there's some work here from Nathan Youngblood, Wolfram Panis, and Harish Bhaskaran, where they're doing it optically with phase change memory cells. But you can see the underlying structure is pretty similar, and also with other systems too. So one thing I'll maybe just say here is these linear weight approaches, they're super good, but they get a lot of their power from sheer scale. So, we've seen a lot of these plots of how big is the set of linear weights you need for computing every year. It's really blowing up. And we can make, people have done absolutely astounding stuff porting this into physics, but perhaps something that, as a community, is still hard for us is really scaling these things up, right? So we can do these. Perhaps if you have like a big kind of industrial behemoth behind you, you can make quite big things, but we're still a way away from the kind of what software wants from us. You also do these in magnetic systems, so two really nice works from the Laboratoire Albert Fair here. This one's pretty chic. You can get both the linear weights and the nonlinear neurons in the same device, and you can also do these super low energy kind of linear weighted sums with skyrmions. So we're seeing these things all over the place. Also, reservoir computing. You're learning a set of linear weights, right? But we know that physical dynamics, I think a lot of us come from kind of community of physicists or as biologists, and we know there's a whole set of dynamics in these systems that are not just linear weights, right? We can do it and we can do it well, but there's all of these rich, strongly coupled, reconfigurable heterogeneous nonlinearities, things like what we saw in the last talk. You can really design these in. And, in addition to the linear weights, can we build network architectures or designs which really directly learn these more kind of heterogeneous, disordered physical dynamics as a direct computational resource? So here's just a little picture of some of the kind of wacky curves, and the reason these are coming down is there's also lots of strong coupling. This was in Toby's talk on Monday. And often, we can kind of tune these things. So quick show of hands, who here works in a physical system where they think they've got some kind of rich, controllable nonlinearity? A bunch of us, right? And this one I'm really interested in. It's a genuine question. Who feels that in their learning system, they're directly tuning that or kind of programming it? Yes, some of us, but maybe a little fewer. Cool. Okay. So I just want to point out a really nice kind of subsection from this really beautifully written review on different ways to train neural networks. So we've seen amazing progress in the devices, really, really impressive stuff in the different algorithms. I think this conference has been a high point of that. But then there's this box here of these other challenges that I thought really resonated with me. So you have this comment here. Most modern neural network architectures are not optimized to make use of the operations most effectively performed by analog physical hardware. Think that's fair? Some nods, some murmuring? And new architectures for ML motivated not by suitability for GPUs, but instead specific analog hardware physics. And then I think I missed a bit that says, we should look into these things. So we'd been thinking in our group where we had because we come from these kind of nonlinear disordered metamaterials things, we had a lot of this stuff, and we kept thinking, is there a nice way for us to make use of it? And it feels like, this is saying something really similar. So I think probably a bunch of us have kind of had these ideas, they're floating around. And here we're looking at actually the architecture, perhaps, rather than the algorithm. How do you chain up? How do you focus your learning onto something that we're probably already quite familiar with, but maybe we've taken more kind of perceptron-based things in a lot of cases and put them into physical systems. So we were thinking about this in our group, and around that time this Kolmogorov-Arnold paper came out. So it's a pretty simple switch. You take your learning from these linear weights, and you have these static nonlinear neurons, and you just invert that relationship. So here, your kind of learned resource is a nonlinear arbitrary function which lives on your edges or your synapses. And then your neurons are just linear sums, something like a Kirchhoff sum or something. So there's a preprint there. And okay, yeah, so that's it. So we were interested, could you do this kind of thing in physics? Would it be perhaps at least a framework? Not saying it's like the best or anything like that, but just a way to start playing with this idea of directly learning these nonlinearities. But there's some tricky things, right? So in the first software demonstration, how did they get these nonlinearities? What they used was something called a B-spline. Splines, anyone familiar with that? Yeah, a bunch of you. So basically, you just have, this is your input space, let's say, your x from like -1 to 1. You discretize that into a grid of G points, and then you can move each one of those points up and down. And then all the spline is a third order interpolation between those points. So often, if you don't have a, yes?
Doesn't that sound a bit like weights with extra steps?
Yeah, precisely. So it's weights with extra steps, and then maybe what we'll see is the things that you can get from an architecture is where you spend your weights with less or extra steps can matter, but you're 100% right. And as you can see, this is obviously going to take more parameters than a linear weight. So you may fairly argue, what's the point? But hopefully we'll see. So yeah, so you have, with each of these grid points, you can move it up and down, you smoothly interpolate, and then that's how you get all these functions. But I think as we know, even though we have all of these nonlinear functions, you usually can't get whatever you want, right? You're usually limited to some set of physical things. So I will say quickly, a shout out to Natalia. I think a few people are starting to have these ideas. So there's a really nice theory or simulation work, I think that's fair to say, of photonic networks also implementing these things. So go take a look at that. So we were wondering, what kind of physical system can we find that could implement, maybe not ever perfectly arbitrary, but arbitrary enough to do some useful computation? And we came onto these. So I was at a conference a little bit like this in 2024 in Erice in Sicily. There's another one this April, so if anyone's interested, it's a nice location, good talks come along. And someone was presenting just a kind of materials characterization talk, but they were showing these. So what they are is, and this was Fabiana Taglietti's talk in Erice, you just take a thin 30 nanometer silicon layer on top of a buried oxide, this kind of silicon-on-insulator technology, and they use a cool technique of doping I hadn't seen before, where you take a polymer with your dopant ion on the top, and then you flash it in the oven for about 1 second, and you get this pretty disordered distribution of these dopants. So then you can hook up a bunch of electrodes to these. There's 8, but we're only using 4 here. The rest could be explored in future, or you can try putting it in different direction through the device. And then if you put some voltage in and measure a current out, those ones are the voltage here and the current there. If you tune these 2 voltages here in the range of just a couple of volts, you get a huge amount of expressive nonlinear transfer functions. So this is pretty cool, and we can actually look. So here, just to say, we've fixed the second tuning voltage. Oh, nice little PowerPoint error there. So we fixed the first tuning voltage at -0.2 volts, and we're sweeping the second one. So that's what's allowing us to get this smooth set of curves. Here, I'm just showing you some more points from the whole kind of nonlinear transfer function surface that we can access. So we have this big range of voltage programmable nonlinear dynamics over a pretty small voltage range. We see things like negative differential resistance, non-monotonic functions, basically just kind of how much harmonic content and turning points. We think that's a nice building block to build whatever you want. And the tech specs are, we think, quite nice. So they run at room temperature, up to 2 megahertz operation, and they say so far because that's where we hit the bandwidth of our transimpedance amplifier that lets us measure them. We've bought a new one. We think it can go at least a bit faster. And then we're looking at kind of fractions of a microampere. So it's maybe 0.1 up to 1 microamps over the range of -2 to 2 volts. So if you run that through, it's running at hundreds of nanowatts and sub-picojoule per nonlinear operation. So here,
what is the basis for your function?
so the base.
Also splines or something else?
Sorry. So this is all experimental data.
Yeah.
So there's really no spline. It's just the physics that's coming out of the device.
But do you know what kind of expressibility this function is?
Do you mean
Complete set, I don't know.
do you mean if I was going to classify them by some mathematical framework, what it would fall under? No, I'm afraid I don't have a good answer for that. The way that we're treating it is this is our set of basis functions. And
I don't know that it's
no, maybe we could talk afterwards. But what we will do is, let's wait a few slides, and then if you're not satisfied, let's come back to it. Okay, and then, you can tune it even more, and you have this really big range of funny curves. So it seems to be quite expressive. But, of course, this is one more thing. They also seem to be pretty stable. So often when you make these things, some of the other systems we've made in our lab, they're nice, but you run them for a few months, and the device gets a bit knackered. You have to make a new one, or your training kind of goes out the window, right? So this is between August and December. We ran about 10 to the 13 measurements through this device, and this is a kind of sample of the IV curves before and after. I can plot the August versus December on top of each other, and there's obviously some noise, but we're pretty happy with that. Okay, but I've shown you a lot of curves, but I think maybe what you were getting at is, if the function we want to make isn't naturally in that set of curves, it's not enough, right? So what are we going to do? So what we decided to do is construct some synapses for our Kolmogorov-Arnold network, where we're putting a couple of these things together in parallel or in series to enrich that set of functions we're getting. So if you imagine you have one of these tunable things, it's like one term in your Fourier series, you can put more until you get what you want. But to do that, we needed some way to train it. So we've used a pretty vanilla method here. We've made a data-driven digital twin. It's just an MLP trained on the experimental data. So here we've got the solid, which is the real data, versus the output of the twin on some of the test set. And it fits pretty good. And the MLP you need is not so big. It's 3 layers, about 200 hidden neurons per layer. Cool, and we can differentiate that. So what we can do now is construct, in Python, a model with kind of sets of our digital twins representing each device, and see what we can learn. So here's an example. So we take 2 of our devices in parallel, so they both get the same input data, and we asked it to learn to make sine pi x over the range -1 to 1. So this is what the system's found. It wanted these 2 tuning voltages for the first device, these 2 for the second one, and we've put some small scaling terms on those 2. And you put those together, and it can do pretty well. So I just want to point out really clearly here, we've got a chip with 20 or 30 of these devices, but at the moment, one of them is wired up. So the guy in Milan who made these things was moving to Turin. All his students and postdocs had stopped. So I had to go out to Milan, wire bond these things up, hook it up to the internet. So I've been running it remotely. But the next step, and we're working on these now, is putting more of these together into a circuit. But right now, everything that I'm going to show you is one device time multiplexed into a network. Cool. So we can do it. So if you like, this is maybe it's coming a little clearer. Our basis function is whatever you can get out of these summed together in parallel or series. So that's nice. What else can we do? So I'm just using 2 devices here. Here's some kind of classic nonlinear activation functions. You can do these pretty well. So this is all experimentally measured at 2 megahertz. This one's nice. You can see that here it basically could find more or less that function within its own library, and then the error gets really low. That's nice. But what if you want to do something that clearly wasn't in the set of curves I was showing you, something with a bit more harmonic content? So then it can kind of do all right. Like, I'm still sort of surprised that those 2 curves together make that. But you might want something higher precision. And then you can increase the number of devices per edge. So they're pretty cheap energetically. They're really simple to make. You can stitch these things together relatively freely. So here I've taken a synapse with 6 of these devices in parallel, and just showing you we can make a range of things. Cool, any questions so far? Hey.
So for each
two tunable parameters.
Yeah.
You just train it on the digital twin with just backprop.
Exactly, super simple backprop. Then we get these voltages, and then we just transfer them. So we're measuring it with an FPGA controlled source measurement unit, and that applies it to the real system.
Would there be any possibility to just evolve them directly on the chip?
I would love to. So I'm going to come to that a bit later. Local learning for these things seems perfect, because this digital twin thing is not scalable. When we have measured the different 30 devices on the chip, they all have qualitatively the same sort of things. You always get NDR, you always get these multiple turning points, but they're non-identical, right? And you don't want to have to twin a massive network. So yeah, I agree. Cool. You can also stitch these things together in series. So before I was showing you some kind of f of x, what about something a bit more complex, f of g of x? And you can make more complex things with pretty high harmonic content, asymmetric things, really sharp bits, kind of flat bits. It's working pretty nicely here. So this is 6 devices there, 6 devices there. Cool. But okay, so we've got something that looks like our basis function. One of the ideas behind this was something I should have mentioned that's important. With the original CAN idea, one of the key findings in their papers, and a lot of the papers that have followed, is you seem to need far fewer parameters than a linear weight network, at least for certain tasks. That set seems quite wide, but it is not universal. So we were like, okay, we have all these nonlinearities, but we know that making like 5,000 devices in our labs is hard. If we can harness that nonlinearity, need a smaller network, for our community it seemed pretty cool. But does it work? Even on these simple tasks, how do we do against an MLP? And the answer here, for a single synapse, is not great. So this is our digital twin results. What we're doing here is we've done function regression over a big set of 13 of the harder functions we considered. And this is our experimental data. So when you're trying to do this kind of function, any type of experimental noise is real bad for you. You're super sensitive to that. Any type of model reality gap between your twin and your hardware. So even though the digital twin seems to be, eventually edging out these quite simple MLPs, in experiment we didn't. But then we thought, okay, one of our synapses doesn't just have to be these devices in parallel. What if we interconnect them? So what we've done over here is just stuck the 2 in series, and here we really get a boost in our expressivity. So even though your noise goes up, so even though it's time multiplexed, all of the experimental noise is real. The only thing we're doing off chip is linearly summing these things back together. We can really outperform by a nice margin the MLPs, and we get a better scaling. So this was interesting, and I wanted to kind of unblack box it a little bit. So we've had really quite a cool, big amount of expressivity metrics. Quick hands up if you had one in your slide or you proposed one. There was more than that. None of you are putting your hands up. But we have this one, and I really like it. So I want to propose this a bit, and we're going to put some code up if people want to use this. What we've done here is we've used an idea of sphere packing that was actually developed by Kolmogorov, and we have taken a PCA space, we've sampled kind of a representative set of nonlinear curves from a device or a synapse or a few synapses, and then we've embedded those curves as points in a PCA space. So here's kind of the three of our biggest vectors. Each axis here is a shape. So one axis might look a bit like a ReLU, one might look a bit like a sine wave or whatever. They're just some shapes. If you just had a ReLU, it would be a point exactly on that ReLU axis. If it's something more complex, it lives around there. And what you can see is this orange curve here, orange point cloud, is 5 devices in parallel. And you can see, there's some expressivity. So that would be this curve here, single synapse, 5 devices. But it's relatively small. Then if we go to just 2 devices in series, we get this way bigger, more expressive point cloud. And then what we're doing here, this epsilon, is you're putting a sphere around each one of your points with a diameter in PCA space of epsilon. And you're saying, how many of my sets of points can have that sphere around them without touching any neighbors? If they don't touch anything, you get a tick. So we had 2,000 curves. When epsilon's tiny, we call that all 2,000. But then as epsilon starts getting bigger, some of those spheres are going to start touching their neighbors. Those two are pretty close, right? So you don't count them, and your packing number starts coming down. So you get this really nice, quite granular look into the expressivity of your systems, maybe a little more than a single number. And so you can really see here, 2 devices in series is way more expressive than 5 in parallel. Cool. So we have some way to actually make a nice basis function. Oops, here we go. you might just want to, and that's the 5 devices in parallel. That's like the top 100 most expressive curves. And that's just 2 in series. And you can see you filled in a lot more of the harmonic content space. So you might want to say, how do I correlate that to performance? So here, I've just said arbitrarily, I'm going to say, what's the epsilon distance? How big is that sphere that you only pack half your curves? And if we pull that out, you can plot it here against the averaged MSE across 13 different hard tasks. And you see you get a really nice correlation. So it does seem to work. You can also check versus the number of parameters you're spending in your network. And you see putting 2 in series, you get a big boost. All right. So how about beyond kind of univariate function regression? Here we're doing something multivariate. So we've made a much more complex function. We have x, y, they each get a function. And then you put another function on the sum of those 2. So we compare, we set up some kind of ground truth training set, sample some points. Then the cool thing is we can look experimentally at the transfer functions we've learned on each synapse. And we didn't tell the network anything about this underlying equation, but it's managed to pull out that there's a cosine 2 pi on x, there's that thing, is that shape there, and it's kind of managed to suss out what's going on inside the system. So you get some kind of interpretability from the synapses. That was one of the big claims of these things in software. And then if we look at the experimental reconstruction, it's pretty nice. A little bit noisy, but that's to be understood. And again, we're outperforming MLPs. So it's worth saying we've got a big inductive bias here. We've constructed our network with the shape of the equation. So take that with a pinch of salt. It's not really a fair test. But if you did want to do this task with arbitrary MLP, it's working kind of nicely. And just to give you a sense of, this is quite hard, this is some cuts across these surfaces with the ground truth and the target. So the ground truth and the experimental data. We can do this on a bunch of different tasks. These look, some of the posters you might have had in sort of nefarious bedrooms you'd hang out in as a teenager. And again, we're seeing these, it's managing to pull out these kind of underlying things quite nicely. I'm going to speed up a little bit. But what about some more classic ML tasks? So, another one, this is some synthetic data set where we're classifying some non-linearly separable data. So we're doing this yin-yang thing. And what I think is really cool is this is our experimentally measured IV on each edge in our network. And you can kind of pull out the symmetries here. So you have your 2 little dots from there. You have these smooth and then sharp boundaries across that bit. And here, this is, we don't have inductive bias. It's maybe a more classic thing. And we're doing this with a much steeper scaling. So this is experimental data for us, and this is software for MLP. So we have the catch of experimental noise, Here, the reason I think that's got better is, noise and model reality gap gets thresholded away quite a lot in a classification task. So here, it's looking pretty good. And we can do a range of these. And if any of you have done these before, they might look quite toy, but they're actually often quite tricky. So as you get these more and more nested boundaries and kind of curvature, it can take quite a bit of an MLP to do these tasks. And you can see that we're getting up to several hundred times fewer parameters and often quite steeper scaling than MLP. But everything I've shown you so far is still kind of toy synthetic data. I do think the function regression is cool. You might be attached to environmental sensors where there's some physical interactions. But let's try to really test it. So we looked here, and this is the last bit. There's a nice data set from NASA on a multi-sensor readings of lithium-ion batteries. So they have 33 different batteries. They're all a little bit different. They have different charging dynamics. And they charge and discharge them 2,800 times. Every time you do it, the battery's getting a bit more beat up. So what we've done is, and then there's 5 voltage sensors. So it's kind of in-domain task. We're plugging voltages into the system. We have the temperature, the current and voltage on the battery and on the load, and the time since the last charge. It's noisy. And then what we've done is we've taken 23 of the batteries as the training set, and then 10 batteries we've never seen during training, and that's a test set. So the task is we just show an instantaneous reading of those 5 sensors, and you need to tell us how long before this battery is completely dead, right? Before you can't recharge it anymore, before it's no good. And you might really care about that as something in space where you can't just go and buy a new battery. If you want to do this task, you might want your sensor to be really low energy, so you're not draining the battery itself, and it's working in voltage. The boring thing is that good performance on this task is a straight line, but this is the line we get. So this is the true time until the end of life of the battery. This is what our system predicted, and we were pretty happy about this. So this is the first point we've got to where we're doing non-synthetic data, and we're able to still have steeper scaling and some parameter reduction versus MLPs. And here we really don't have any inductive bias. We have the, I'm sure our noise can get better, our model reality gap can be shrunk down. And what I really want to do a bit more is look into the shapes it's learned and try and compare them against the physical equations of lithium-ion batteries to see, has it actually pulled out some of the dynamics? Let's see if this one works. I also tried running a drum machine through it. Oh, it's quite quiet. I'll play this to you afterwards if anyone's interested. But it sounds really cool. So cool. We've shown that we can learn some nonlinear functions mapped onto tunable physical dynamics. And it's maybe an interesting alternative to linear weights for our community. A CAN architecture, is a nice place to explore this, but I'm sure we can do better, right? That's one example from software. We can develop something more kind of physics explicit. And a neat thing here is it seems to harness what we're good at, rich, tunable dynamics, and maybe help us with what's still a challenge, needing really big networks. So if your physical system seems promising for this and you're interested how to implement it, we're super happy to share code, chat, whatever you like. And also, we would love to implement local model-free learning because the learning we're doing here is not scalable. You have 1,000 of these things, you want to kind of nudge it, and if you're interested to have a chat, please talk to me. So thank you very much, and sorry for running a bit over.